start our discussion for today. So as you can recall, we were having a discussion on the governor mechanism. So last two classes we had those assignment presentations, so somewhat the flow was broken. So I'll just quickly review what we discussed. So we started with the discussion on this governor and the underlying principle of speed loop and how it is related to frequency, power and frequency characteristics. Then we looked at the basic operating principle of the governor and how it controls the power input by controlling the valve of the prime mover. It controls the generator output and hence controls the frequency in the desired range. Then we looked at this detailed block diagram of a governor and we looked at the evolution of governor mechanism from a mechanical hydraulic type to electrical analog type and then finally the digital governors, which are the state-of-the-art representative. And then we took sort of detour to understand some basic concepts related to frequency control. And we discussed about the primary and secondary control functions in a grid in terms of the frequency control. We discussed this graph, the primary response and secondary response. And then we looked at the elements of the control loop. So we were discussing in the last class on this particular point. There are these three components or elements of a real control loop, which are the proportional, integrator and the derivative part. So proportional and integrative control we had discussed last time. And as we saw for proportional, the overall stability and performance was good, but the only problem was that there was an offset in the output. So that means the final value was having some offset, some difference from the desired value. Whereas with an integral control, the offset problem can be resolved, but the stability is not so good. So usually one of the common combinations which we will encounter in control mechanisms is the PI controller. So proportional and integral control, if they are clubbed together, we get the advantages of both. That means the offset is also not there and stability is also relatively better than integral control. So PI is one common type of controller having proportional and integral components. And then the third one, derivative control, is another aspect of it which we'll discuss now. So derivative control, as the name indicates, it is based on the derivative of the input error signal. So mathematically we can put it like this format. So if you have some error signal ET, the controller output AT will be some constant KD times d by dt of ET. So it depends upon the rate of change of the input signal. But this is very tricky because as we understand, if you look at the derivative of a curve, it is the rate of change of the slope of that curve at a point on that curve. So derivative control is the rate of change of the error curve. We would never use control based solely on the rate of change of the error signal, because if the error were huge but unchanging, the correction would be zero. So that's a very intrinsically, by definition only, that is a drawback with this type of control system, having this type of control function, is that if you have a very large error but it is not changing, it is constant, then the derivative is zero. So obviously there will be no control initiated. So on its own, independently, derivative control can't be used due to this particular simple reason. So usually either this derivative control is coupled with the proportional control and you have what is known as the PD controller, or even better is that if you integrate it with the PID controller, the proportional integral both, because if you only integrate with proportional, then still the offset problem remains. So the best combination will be when you have proportional, integral and derivative control. So derivative control, what it does is that it improves the dynamic response, the time taken to settle down, time taken to reach the final output. So that way each one has its advantage. Proportional control gives a stable and robust mechanism in terms of the control mechanism. Integral control helps you cut down the offset, and derivative control improves the speed of response or the dynamic response. So the addition of the rate control to the controller makes the loop more stable if it is appropriately tuned. Since the loop is more stable, the proportional gain may be higher, and thus it can decrease offset more than one proportional action alone. So if you have a proportional and derivative controller, then with the addition of derivative controller, because of the extra stability which you get, it's possible to increase the Kp constant higher. So that's why what it is saying here is that the offset is decreased further. So as compared, if you compare just a proportional controller and a PD controller, the offset will be lesser in a PD controller. But it will not be eliminated entirely. So that way. But finally, if you couple all these three together, if you have PID controller, which is like the best one in terms of these three control mechanisms, so we get the most complex control algorithm, and but it's also used routinely. So it gives rapid response, exhibits no offset, but it is sort of difficult to tune because you have these three different parameters, Kp, Ki, and Kd. So it's like you have to balance all the three in such a way that all the performance criteria are optimized. There is no offset, the speed of response is also good, and the stability of the system is also good. So it often requires extensive and continuing adjustment to stay properly tuned. But when it is properly tuned, it offers a very good process control. So PID is like the state of the art in terms of these three control mechanisms. So usually PID is the most preferred one. And if you want a more simpler version in terms of the complexity of the control loop, then PI might be the second best option. So this figure here just gives you some particular idea in terms of a graphical form that how these control mechanisms they work. So if let's say if your engine is operating at some constant speed and suddenly the load is increasing, suddenly there is load jump. So obviously there will be a drop in the speed. So how these three controllers will react is that if you see proportional, it will give a proportional output proportional to what is the drop, and it's like a step function. Whereas integral, as we understand, that will depend upon the area under the curve. So usually it will have this type of thing. It will rise and then settle down to a particular value. It's slower in response, but ensures that the offset is not there. And derivative is just at the point of change, because whenever there is a deviation, whenever there is change in the signal value, there is an error only, then only this will exist. And as you can see, it's like a spike just at that particular moment. So it's a push to the response by increasing the speed of the response instantaneously. So that way these three controllers are there, and if you want to compare the operation, as I said, the PI and PID are the most common ones. PID is the best one, but slightly more complex as compared to PI. So if you compare these three, this is how they can compare together. So you have your uncontrolled variable going like that, and now let's say if you applied a proportional type controller, what will happen is that now you want its desired value, let's say, to come to 0. So let's say this is the error variable. So this is the error variable, and you want to reduce obviously the error variable to 0. So if you let's say implemented a p-type controller, what it will do is that this step type response it will have, and then but it will settle down with some offset. It's not going to 0, rather there is some offset which is existing. Yeah, better than that is the PI controller. With that integral action coming into picture, the offset is going to 0, but as you can see, there are more oscillations and it is gradually settling down. Whereas PID, this third one here, this you see with the addition to derivative control, the speed of response is fast and more stable also. So it just there are not many oscillations, it just rises and quickly settles down to the final value. So that way, PID response is the best one, but PI is the second best. And practically, these two are the most common ones which are used, PI and PID.
Sir?
Yes.
Hello? Sir,
Go
your
ahead.
voice volume is too low, sir, actually.
It's low.
Yes, sir.
Is it better now? Any better?
Yes, sir. Now it's better, sir.
Okay. Any questions on this? The PI, PID controller? Control mechanisms?
Yes, sir.
Yes.
Sir, suppose if we have a very responsive and unstable system, so should we use derivative controller because it will instantaneously control the fluctuations if they are?
Yeah, so as we said, derivative is not never used on its own, because on its own it doesn't have any meaning. Only responds to changes in the result. So ideally it should be PID, the three together, or second, I mean, if you want to improve just the response, but then if you can do with the offset, then you can go for PD controller also, but that is also not really preferred, because offset is something which we want to avoid. We don't want to have an error at the final settling.
Yes, sir.
See, so usually PID or PI are the most common ones. Anything else? Anyone? Okay, so let's move ahead. So now we'll look at a classification of governor in terms of its modes of operation. So far what we looked at, if you just try to relate, if you see, this was the evolution of governors. I mean, we first discussed the basic principle, what is the basic operating principle and the conceptual understanding. And then what we discussed, this was a evolution. It's not really a classification in terms of the governors which are available at present. It's how the governors have evolved over the period of time, and finally we have the digital governors. And then we looked at some more fundamental concepts in terms of the control functions which are needed for frequency control and the types of controllers which are available. So now let's look at the actual classification of governors in terms of their modes of operation. So how they behave, what type of mode of operation they work in. Based on that, there are two types. The first one is known as the isochronous governor. So as it says here, it is the simplest type governor, controls and maintains the frequency regardless of the generator loading. So as you can understand, very simple one. I mean, in terms of even if the loading is varying, it has to just keep the frequency constant. So an isochronous governor keeps the frequency constant independent of the generator loading, that is zero droop. Because if you recall what we discussed earlier also, the typical power frequency characteristic is something like this. So in response to the change in the loading, the frequency should change. So that is the, expected way. But here we are taking a simplistic assumption is that even if the power loading is changing, frequency remains constant. That means there is no droop. So it will be, if you plot the characteristic, it will be just a horizontal line parallel to the x-axis. So this type of governor, it adjusts the prime mover's valve to bring the frequency back to its set point value. So there is one set point value, it just maintains at that value. There is no droop sort of thing. This governor mode is also referred to as frequency control operation mode. That is another name for isochronous mode of operation, frequency control operation mode. Now, the application, as you can understand, this is not really a very practical thing in terms of a practical power system. So it has got a very limited application, and as it says here, such governor works satisfactorily when only one generator in the system has to respond to changes in the load. This type of governor is problematic to use when several generators connected to run in parallel have to share the load in the system, because they can work against each other trying to control the frequency to their own settings. So it's you can say more of a hypothetical case in a present day power system. So basically, if you have isolated generator and some loads connected to it, there are no other generators in the system, just one generator and its loads. So that in those applications, isolated applications, one can have this isochronous governor mode, because there is only one generator, irrespective of the load fluctuating, you want to keep the frequency constant. So only for that particular application this might be used. But whenever you have a larger system having more than one generator in that particular system, so as you can understand now, it will be an interaction between these different generators, and according if the load shifting is there, then accordingly the set point of the individual generators might need to be changed, because you want, there will be a redistribution of the load in the system. So whenever there is a change in the loading, there will be a redistribution in the load allocated to each generator, and accordingly some particular generators might need to shift their frequency up, some might need to shift their frequency down, and also the amount of the magnitude by which the set point needs to be shifted up or down will be different for different generators. So in that type of a mode of operation, which is actually the practical power system, this will not be functional. So isochronous governor is more of a conceptual thing and having application only for a isolated generator, having only one generator in the system. So the model for this is very simple. I mean, this is how you represent the control loop here, that there is some delta omega. Now this delta omega will come by sensing the speed or the frequency, as we discussed here earlier in the first block diagram. So delta omega is nothing but your omega minus omega ref. So whatever is the actual omega, you measure that, and minus whatever is the reference omega. That omega minus omega ref is what is the delta omega coming here. So that is the delta omega, which is coming as an input to the governor, and for sake of simplicity, a simple PI type controller has been put here, and corresponding to that delta omega, the delta P fuel will change. So this block diagram which we are showing in isochronous governor mode, as you can understand, it is only a portion of this entire loop. So only this portion is what is being shown there. So you have delta omega, which is nothing but omega minus omega ref, and P fuel going out. So basically there is no P reference here. So for isochronous governor, there is no need of a set point, setting of the set point in terms of the reference power output. Why? Because as we said, irrespective of the power loading, it just has to maintain frequency constant. So there is no concept of P ref here, only the delta omega and P fuel is the output. So only this portion is being highlighted there in terms of the block diagram given here. So it can be implemented, as we discussed, with a PI type controller. So Kp is the proportionality constant of the proportional controller, Ki is the proportionality constant of the integral controller, and when you put integral in the S domain taking a Laplace transform, then that integral becomes as Ki by S. So as you can notice, the isochronous generator, this should be isochronous governor, not the generator. So the isochronous governor has only as input signal the deviation of the speed delta omega. That is the only input, and that is delta omega is the difference between the measured speed and the reference synchronous electrical speed omega E0. This speed deviation is amplified and integrated to produce the control signal. So if you have a PI type controller, amplified and integrated to produce the control signal delta P fuel, which actuates the throttle valve of the prime mover. So then this P fuel goes as the input to the valve control mechanism of the prime mover. So as you can see here, this P fuel is going to be input to the prime mover. So that delta P fuel goes as input to the actuates the throttle valve of the prime mover. The steady state operation for an isochronous governor is defined by the condition delta omega equal to 0. So obviously when the steady state is there, when the load variation is not there, then delta omega will be 0 and delta P fuel will be 0. And if you want to plot the frequency response of a generating unit equipped with isochronous governor, so this is the type of frequency response you'll get. So you have some nominal frequency value corresponding to your frequency. You can define an electrical angular speed omega n. So it is just constant there. If there is a load shift, if there is a sudden load increase, then the frequency drops. But then the governor action is such that it brings it back to the delta omega equal to 0 point. So this line will always be constant. I mean, this line will not shift. That is the characteristic of the isochronous governor. It will just be operating at a constant value of your frequency. So this is, as you can understand, this is more of a theoretical consideration, only having application only in an isolated system, having just one generator. In all the other practical systems, whenever you have a larger power system, you will always have maybe several hundreds or thousands of generators which will be operating. So for those modes of operation, what we need is known as the speed droop governor, which is like when you say governor, usually you imply the speed droop governor, having that drooping characteristic. So the speed droop governor controls the frequency, taking the generator loading into account, as we discussed, that power frequency characteristic. So if loading increases, then the frequency tends to go down. So you need to shift the reference value so as to get the same frequency. So it provides the primary control function. It is utilized when two or more generating units connected to the power system have to share a load change. So for all practical applications, we have minimum two or more generators. Speed group governor will be used. Speed group governor has a characteristic with a negative slope. We have already discussed that. If you plot the frequency versus power, it is a negative slope. It reacts to load variations by changing its speed. Namely, it controls the relation between power and frequency. This means that a higher power output is established when the frequency drops, and similarly, a lower power output is established when the frequency rises. So that's understood. Whenever the frequency is dropping, you increase the power output. If the frequency is rising, then you cut down the power output. So the model for this is something like this here, slightly more complicated as you can understand. So delta omega is coming here. Again, the same way, omega ref, your omega minus omega ref will come here, delta omega. But you have another, control loop coming here, another feedback loop, which is corresponding to your delta P ref, the reference value of the power output. So this is what helps you adjust the setting of the no load setting, the no load frequency point or the reference point. So if you look at a simple example, suppose if you don't want to change the delta P ref, if your the setting of the reference power level is same, delta P ref equal to 0. So what it will imply is that at this summer here, delta P ref is 0 and only delta P fuel is fed back, and this is positive, so it comes here straightforward. So at this summer, the thing coming from the left hand side is delta P fuel multiplied by R. So this delta P fuel into R is coming here, and then you have delta omega coming here, and both these are, as you can see, positive. So you get delta omega plus R times delta P fuel. And if the system is operating under steady state, then you have this thing going to 0 because you don't want to change this. And if there is any change in the delta omega, accordingly the delta P fuel can be adjusted given by this relationship, and as you can see the negative sign, that implies that if delta omega is increasing, then delta P fuel will reduce. If delta omega is reducing, then delta P fuel is increased. And this constant R here, that represents the droop of the characteristic. What is the slope of the characteristic? The speed droop governor has two input signals, namely deviation of the speed, delta omega, and the deviation of the power set point, delta P ref. So this is a practical consideration, and all practical governors will have this thing. Two settings. One is the delta omega, the omega ref, which will result in delta omega, and one setting for the reference power, which will give you the delta P ref. So the steady state operation for a speed droop governor is defined by this condition. If frequency drops due to, example, an increased load, the speed droop governor will yield to an increased delta P fuel, which will be in order to the prime mover to increase the power output, and vice versa. Speed droop governors are utilized when multiple generators have to share changes in load in the power system. For this sharing to be equal, the speed droop governors need to have the same droop characteristic. So if you have multiple generators operating in the same power system and the frequency has to be maintained constant, all these will be connected in speed droop mode, and the droop characteristic, the slope at which they are having their droop, should also be similar. They should have the same droop characteristic to ensure that there is the equal sharing of the load amongst them. So if you compare the droop characteristics of these two governors, as we said, the isochronous governor is like this, just a flat characteristic, irrespective of the power loading, frequency remains constant, whereas speed droop governor is having this type of a negative characteristic, negative slope. So any questions so far? Okay, let's move ahead. And so if you look at both these implementations, what we had, for sake of simplicity, basically we just worked with a PI controller, both for the speed droop governor and also for the isochronous governor. But most of the modern digital governors and all, they will have, usually the electronic governors and digital governors, they will have the PID algorithm. So accordingly, this will be slightly modified. This block here, which is representing the control mechanism in terms of PI controller, that will be modified to a PID controller. So this PID controller will have this type of a characteristic, as we have discussed also. So it will have all the three components. So your ET here is the error as a function of time, and your Kp is the proportional constant, Ki is the integral constant, and Kd is the derivative constant. So the final controller output, that will be a summation of all the three components. So there will be a proportional action, there will be integral action, and there will be a derivative action. And the final is the summation of the three. And when you have a digital governor, which is, as we said, is the standard these days, then this equation, as you can see, is in the continuous time variable mode. But for a digital system, you need to discretize this particular equation, take the discrete equivalent. So if you take the discrete equivalent, proportional remains same. Just multiplied by a particular constant. What was integral in the continuous domain, that becomes a summation in the your discrete time domain. And what was the derivative in the your continuous time domain, in the discrete time domain, that becomes as a the successive difference. So here, as you can see, now t is the sampling interval. So how frequently you need to sample, that again depends upon your computational ability. So the computational capability which is available in terms of the governor mechanism, what type of controller you are using, what type of how many cycles per second it can perform in terms of the the control mechanism, the calculations and all. So depending upon the if these days we have very good control mechanisms which are available, computers which are available. So that way the sampling interval can be very small, but the sampling frequency can be very high. It can be kilohertz, megahertz range. So there can be a lot of samples which you can collect, go on collecting. And so what is happening here is that if you are having the ith sampling interval, the error in the ith sampling interval is EI. So the output of the ith sampling interval is nothing but your constant times the error at the ith sampling interval, plus you have the integral control, which is nothing but a summation of the errors from the previous time instance to this particular instance. And then you have your derivative control, which is nothing but the successive time difference. So at the ith time interval, this derivative is the error at the present sampling interval minus the error at the previous sampling interval. So that way the PID control can be implemented in the digital mode of the governor. So practically this is what we use, PID controllers in the digital mode. So your this governor, this block diagram here will have that discrete PID controller equation that will be coming in picture here.
Sir, this is Prashant.
Yes, Prashant, please go ahead.
Sir, in that digital or discrete equivalent, that in integral part, the summation is from j equal to I to I.
No, that is, I think, a mistake. It should be, j equal to previous time instant. So from wherever you are setting the reference, it should be from there.
So what should we write, sir?
It should be, how you define the instant, usually it should be j equal to 0. So it depends where you set the reference. So usually what will happen is that the reference will be at the point when there is a shift in the load. So if there is a shift in the load, then you define that as the 0th time instant, and then you keep integrating till the time you get back to the stable operation.
And that EI, sir, is EJ, I think. Sir.
Yeah, that will be EJ. Right.
Yes.
Yeah. So this is, this can be corrected. This is maybe just a figure, so we'll correct it. Yeah. So because the error will come into picture only when there is a shift in the load. So whenever there is a load shift, then this will start, the integral action will start. So j equal to 0 will correspond to shift in the load, abrupt change in the load.
That means, sir, it is starting from the instant when the load is shifting to the ith instant.
Correct.
Okay.
So this will be there. Anything else? Okay, so this will be the standard PID algorithm which is used in the digital governance. Now, performance requirement. I mean, whenever you define a system, we looked at how the system is operating. What is the? Yes. Who is that?
Souvik.
Yes, sorry. Go ahead.
This capital T sampling interval. Is this a constant particular value? That is, suppose we take 0 to 15, we take 5 to 20. Is it like that? Sampling interval.
No, sampling interval will depend upon the, as I said, the computational ability. Okay, so whatever is the sampling frequency, the inverse of that will be the sampling interval. And the sampling frequency will be higher, the better you have the computational ability, the higher will be the sampling frequency, and smaller will be the sampling interval.
That is for quick response, correct, sir?
Right, very good. Very good. Anything else? Any other questions? Okay, so let's move ahead. So we looked at the basic operating principle and the type of controller, the control mechanisms in terms of the components of the control mechanism, and then the overall thing. Now, whenever we have a system which is operating under some particular conditions, we always, ideally or practically also, we want to specify the performance requirement. So when will we consider that this particular governor is operating in a particular, in the desirable manner? We need to define it beforehand. So as we understand here, the main function of the governor is to maintain, in terms of a hydro turbine governor we are talking about. So the function is to maintain the water turbine generator speed regulated in spite of variation of load. So that is the functionality. Now, as you can understand, you have this speed regulation is the basic function here. So as you can understand, if there is a lot of fluctuations in the load, the controller will also try to adjust the frequency of the speed of the rotation of the turbine accordingly. So there are two things here. One is that your controller should not be too sluggish, that there is a lot of change and it is not really able to catch up with it. That is one end of the spectrum. Another end of the spectrum is that it should not be too over responsive also, that like sort of overfitting the curve. That means if there are a lot of fluctuation, it is also following each thing very minutely. So ideally you need to specify that in terms, because if there is a lot of the control mechanism is also very quickly, it's responding and having a lot of changes, then stability might become an issue. So the stability, usually when we talk about the performance requirement, we need to take care of the stability of the overall system in terms of the particular control being rapid also in terms of the speed, as well as stable in terms of not having a lot of too many oscillations and all. So the stability in this case we define is given here. The governor system should also be capable of controlling with stability the power output of the turbine at all power outputs between 0 and maximum power output, inclusive when the generator is operating in parallel with the other generators in a plant or in a transmission system, or when operated at rated speed with isolated load at all power outputs to and including maximum output of the turbine. So what it basically means is that speed control is there, but it has to be in a stable way. So stability is an important criteria. And in both the conditions, one condition is that when your generator is operating in parallel with other generators in a plant or in a transmission system. So maybe in a plant also there are usually 3-4 units are there. So all of them are operating in parallel, or all these generators are now part of a larger power system connected to transmission network, and they are sharing the load amongst themselves. So under that condition also, as well as if a particular generator is operating in isolated mode just with its own loading, in that mode also. So in either mode of operation, the stability of operation should be ensured. So there are some guidelines given here in terms of the how much oscillations are allowed, and it is recommended for stability of the overall generating mechanism. So first, let's look at the criteria for the mechanical governors, just for sake of completion. As we understand, these days we are having digital governors, but still, we just to give a reference. So for mechanical governors, the criteria is defined like this. The magnitude of the sustained speed oscillation caused by the governor does not exceed 0.3% of rated speed with the generator operating at rated speed and no load, or operating at rated speed and isolated sustained load with the governor speed group set at from 2 to 5% AQC. So what it means is that there are these two conditions. The first clause A is talking about two conditions. One is that when your generator is operating at rated speed and no load. Okay, so it is operating at the rated speed but without any loading in that condition, or if it is operating at rated speed and isolated sustained load. So there is sustained loading, but it is an isolated mode of operation. It is not operating in parallel with other generators. No, that isochronous type of mode of operation. So in either of these two conditions, if it is operating at no load or it is operating with a sustained load but in isolated mode, the oscillations which are resulting by the governor control action, the magnitude of the oscillation, speed oscillation, should not be more than 0.3% of the rated speed. Okay. So suppose, for example, let's say if your synchronous generator which we are talking about is having has having 10 number of poles and frequency is 50 Hertz, then what will be the rated speed? Rated synchronous speed? 10 pole machine operating in a 50 Hertz system. Yes?
So 600 RPM.
Right. That should be, that equation should be always at the tip of your fingers. You know that synchronous speed equal to 120 F by P. So 120 into 50 divided by, we said number of poles is 10. So you get 600 RPM. So let's say, suppose example, we are taking this particular generator having 10 poles operating in a 50 Hertz system. So the rated speed of this generator is 600 RPM. So now what it is saying is that let's say your generator is operating under no load condition or with a loading but in an isolated mode of operation without being connected to any other governors, any other generators in the system. So under these circumstances, if there is some fluctuation, so usually at no load, basically the loading is not there. So only condition will be that there is a sudden load which is put on, or if the sustained load is there, then it can occur in either way. Either the load can increase or the load can decrease, either way. So under these conditions, the oscillation which is caused due to the governor action, if you want to look at it graphically, these are the oscillations we are talking about. So because this governor, suddenly there is a change in your loading. So in response to that, the controller will act and there will be these oscillations which will come into picture. So the magnitude of these oscillations, as it says here, the speed oscillations, those should not be more than 0.3% of the rated speed. So if you have 600 RPM, how much is 0.3%? Around 2 RPM, right? 1% is 6 RPM.
1.8.
Right. So 1.8 RPM, as you can see, it's very stringent norms. So even with a mechanical governor, that type of norm is expected. So if you are having any shifting, this and generator operating speed is 600 RPM, the oscillations which are caused should not be more than plus minus 1.8 RPM. Then the second condition is given when you are having the generator operating in parallel with, and yeah, one more point was given here, that speed group has to be in this range. That means at the rated speed, the rated power output, the change in the frequency or the speed from no load to full load, the speed group, you can always recall this thing. That is how you define the speed group. That is the no load speed minus full load speed divided by the full load speed. So at your rated power out, what is the full load speed? And we can refer this law in terms of speed. So at the full load or the rated power output, whatever is the full load speed, that is NFL, and no load speed is null. So this particular slope of this speed group characteristic should be such that this value NNL minus NFL divided by NFL should be into 100 should be 2 to 5%. That is the recommended range. So within that you can set the speed group characteristic. So that is for a mechanical governor. The speed group characteristic is between 2 to 5%, and the variation in terms of the oscillations of the speed should be in this range. And the second case now, it says here the magnitude of the sustained power output oscillation caused by the governor does not exceed 3% of the rated capacity of the turbine, with the generator operating under sustained load demand in parallel with other generators, which are themselves capable of operating in parallel with other generators, and with the governor speed group set from 2 to 5% increase. So that is the second case, which will be practically a more practical case, is that when you are having your generator connected to separate, through a particular transmission network, it will be connected to several other generators. So your overall power system is having a n number of generators, and each generator is capable of operating in parallel with other generators. In such a condition now, because as you can understand, now the system is more complex, because earlier it was very simple. You only have your own generator and you just need to set its particular frequency and the operation is simple. But here it is slightly more complex, as you can understand, because if there is a load change, so this load will be redistributed amongst all these generators, and sometimes some generators will have to increase, some will have to decrease their set point, some will have to increase by a higher value, some will have to increase by lower value. So a lot of other possibilities are there, combinations are there. So that's why here the norm is slightly less stringent. So in such a condition, it is allowing for a 3% of oscillation in terms of the rated speed. So if for the same example which we took earlier, if you have a 600 RPM rated speed, now 3% means 18 RPM. So you can have plus minus 18 RPM fluctuation can be allowed. And this again, so all these generators should have their speed group in the range of 2 to 5%. That is the range of the speed group value. So these provisions are given in IEEE standard 125, and if you look at so this is for the mechanical governors, just for reference. I mean, these days we don't use that, as I said. So now what we use mainly are the PID electronic governors, and in this case, let's look at the stability criteria. It says here, the governor operation shall be deemed stable if peak to peak magnitude of the sustained load oscillation caused by the governor with 4% or more speed group setting does not exceed plus minus 0.15% of the rated capacity, the generator being connected to the grid with sustained load demand. So now, as you can see, the criteria is more stringent. So even for the generator which is connected to the grid in parallel with there are several other generators, for such generator also now the oscillation allowed is only plus minus 0.15%. So for your 600 RPM machine, how much will be this value? Like 0.9, right? Plus minus 0.9 RPM. And so it's very stringent, as you can see. So that is also, you can understand, that is an advantage of the electronic governors, that they have a very strict range of operation as compared to a mechanical governors. So for a mechanical governor with grid connection, it was 3% range, whereas here it is only plus minus 0.15%. So very stringent characteristic. And also the speed group now they define in terms of, earlier it was range of 2 to 5% given, but now the standard says that it should be with 4% or more speed group settings. So up to 4% or more is allowed. So that way. So the stringent, it's very stringent, and that's another advantage of the electronic governor. You can expect a much tighter variation. The oscillation will be very less, and much stringent operation can be expected. Then for some other things, it says here that the governor shall control with stability the turbine at any speed between 85 and 105% of rated speed when operating isolated from the system, and while connected to the system at any load between 0 and the load corresponding to the maximum opening of the guide wings. So in terms of an isolated system, if you don't have connected to other generating options, other generators, then the range is much more flexible. And the third point, with the turbine running at its rated speed, the total amplitude of speed variations not resulting in any measurable difference in the guide apparatus servo motor position shall not exceed 0.02% of the rated speed at any gate opening. So what it means is that when you are having the machine running at the rated speed and without any load change, it's going in a stable fashion, then what you want is that the fluctuations which might be due to some stray reasons those should not be more than 0.02%. And in case there is a load shift, load change, then also it should be within the plus minus 0.15% range. So that way, the electronic governor is having much more stringent norms and much better functionality and capability. So that's why you can understand this is what is recommended these days. And now coming to the last point in this governor thing is just one particular compilation in terms of what type of governors we used in India for different hydropower plants. So if you see, there is a range of hydropower plant capacity. So if you have a micro hydropower plant that is up to 100 kilowatt, this is, I mean, many times you will see there also now, because now the computational things, the computational infrastructure is coming at a much lower cost. So these days there is a tendency to use the governor system even for smaller plants. But traditionally what is there is that this governor mechanism, as you can understand, is very complicated control mechanism. It's not really very cost viable for very small power plants up to 100 kilowatt range. So traditionally what has been used is that for these plants which are in the micro hydro range up to 100 kilowatt, we recommend, there has been recommendation of using digital speed control system with load actuator. We will look at this in the next class. That means instead of changing the flow, changing the turbine guide vane opening and changing the flow of water, we don't change that. Rather, we change the load. So this is known as the ELC, or the electronic load controller. We will look at this in the next class. So this might be recommended for a small generator up to 100 kilowatt range. Is that, because the control mechanism and the computational infrastructure is more expensive. So instead of, you don't change the load only. You don't change the flow. So you don't change the power flowing into the turbine and the power generated. What you do is that rather, if you are having extra power, then you do some sort of a load adjustment. So that is known as electronic load controller. We'll look at that in the next class. But for all other power plants, all other generating units greater than 100 kilowatt range, we use the governors, and there is slight variation. So for if you have a small hydropower plant, typically up to range of 3 megawatt. So for these, we use flow control governing system with hydraulic actuator and digital PID speed and power control system. Mechanical motor type actuator has also been used up to 1 megawatt unit size with microprocessor based control PI controller. So for smaller systems, a mechanical motor type actuator can be used, but for larger systems, usually it's a hydraulic actuator which is used. And for small hydro above 3 megawatt, invariably you have a flow control PID governor with hydraulic actuator. And the large hydro, which is defined as about 25 megawatt, for that, usually the standard is to have this programmable logic controller, PLC based flow control, PID governor with hydraulic actuator. So that is the different types, different variants. And the smaller one, the load actuator type system, that we'll discuss in the next class, known as the electronic load controller. For all these other generating units greater than 100 kilowatt, the type of governor mechanism which we have discussed in the previous classes, this has been the flow control governing mechanism is what is used. Okay, so this is all the discussion on the governor mechanism. Any questions, anyone? Okay, so we will stop here. By the way, one particular